To find the slope of the tangent line, you will find the derivative, and then you have to find the value of the derivative. For example, we will find the root of the function by, it's still dy dx, because x and y are being identified with a parameter. So we wanna find the derivative of tangent line, slope of the tangent line. You still use the first derivative with respect to the x variable. So derivative of y is sine t, derivative of x is 1 minus cosine t, and then you plug in pi over 4 to find the slope. This is the calculation of the slope of the tangent line. Once we know the slope of the tangent line, we could determine equation of the tangent line. But right now, we just want to find slope. Calculation. So first you would derive the formula for the derivative. The dy dx. And you find derivative of y with sine t. Derivative of cosine is negative sine t, but there's negative cosine, so derivative sine t. And derivative of the denominator should be the derivative of x, and that will be 1 minus sine t. So we find the derivative separately. The derivative for x divided by the derivative of the x, and that's our function. But the actual question asks for a slope. So you have to make p equal to pi over 4 and then calculate slope. So slope is, say, m equal to sine pi over 4 divided by 1 minus cosine pi over 4. So the slope calculation is the evaluation of the derivative. Okay. Sine pi over 4, cosine pi over 4, 3 pi over 4. They both equal to root 2 over 2. So we have root 2 over 2. And this is the 1 minus root 2 over 2. All right, so we can barely match with any number. But starting here is evaluation. You can try 2 different methods. Number 1, you use your calculator to find this fraction in decimal form. And you compare the decimal number for the A, B, C, D. And that way you can see which one matches the number that you have. So find decimal number, and then you can compare them with a decimal value. That's one method. Another one is you actually go into the algebra of this fraction, simplify it. Because after it simplify, it will match one of those. So the simplification is the key. And you see, we have a complex fraction. Normally what we do is multiply denominator and numerator with the denominator for time 2. And then time 2, because 2 obviously is a denominator for both the fraction and the numerator and denominator. After we multiply 2 in the numerator and denominator, we will get root 2 in the numerator. And we'll have 2 minus root 2 in the denominator. So when you do this, it get rid of the fraction. So become from a complex fraction into a simple fraction. But then we have roots. Normally, we do not wish to have any roots. So there's another process which is called a conjugate. So we want to handle the denominator. You multiply numerator and denominator by the conjugate of the denominator. The conjugate of a root form is we change the sign. So we multiply 2 plus root 2. And that's something we do in college algebra. You would multiply the conjugate to the numerator and the denominator to keep the form but make it simplified. All right, the purpose of the conjugate is after this multiplication, notice that a minus b multiplied by a plus b actually equal to a squared minus b squared. That was a formula. So now we have a minus b, a plus b, a equal to a squared minus b squared, which the square will get rid of the root. So it's going to be 4 squared, 2 squared minus root 2 squared. So that's 4 minus 2. So obey that formula. So the denominator was simplified. Now, what was the numerator? Numerator will be 2 times root 2, which is when you multiply these two. And then when you multiply these two, it's root 2 times root 2, which we get 2. Okay. From here, you can see the denominator is greatly simplified. Denominator becomes 2. Numerator is 2 root 2 plus 2. All right, and then we divide both of them by 2. You see that one simplified into, right? And that will be the final answer. The 2 will be a common factor in the numerator and denominator, so we cancel the 2. Divide each term by 2, you see the final answer. Okay, so I think that should achieve simplifying it in the end. So here we are. Let's see what we are answer. Right, if you are in the online classroom, let me know if you have your page. Okay, let me copy the link over. If you can, try to mark the link. So each time when you're attending online, you need the same thing. Anyone else? If you don't have your link, please let me know. Right, if you haven't really submitted, let's see. We finally get here, right? So this number is 2 root 2 plus 2 divided by 2. Now, based on the relation with fraction, if you have a such as b over c over a, it would equal to b over a plus c over a. That's a rule with fractions. When you add fraction, you add the numerator and keep the denominator. That's from here to here, and we can go back and forth because they're equivalent. All right, with our calculation, we add, we'll get 2 root 2 over 2, following this pattern, divided plus 2 over 2. So that's really 2 plus 1 after we cancel the 2 in the denominator. Right, and that'll be the final answer. Let's see. Right. So final answer for the question should be B. Anyone else not having your link? Alicia, maybe I'll call you. Do you have any homework question you want to ask? Any homework question? Okay. So I keep the scanner on. If you haven't really submitted, you can submit after click out your final answer. Right, so let's move on to the next section that we were working on last time. We've been working on bullet points. Right, we're up to the part where we talk about conversion to full equation and rectangular equation. Right, 9.4, we introduce a new coordinate system. If you're new to polar coordinate, maybe we can review what we're doing last week. All right. Basically, polar coordinate is using a pair of number two numbers to represent a point. So it's called coordinate. It's like a coordinate system allows you to locate a point. Polar coordinate is more popular when you travel at sea. When the rectangular coordinate is hard to get, I like anchor a point and identify how far you are from, like, see, that's your boat and that's somewhere along the coast. So it allows you to identify the direct distance and angle to that location, right? So in the polar coordinate, we have one distance measure, which is the distance r, represented like this is the radius, and then the one angle angle information, which is the angle theta, right? So in the polar coordinate, you identify a single point that you are connecting to. So from the point P to point O is being called the pole, like the North Pole. And then we identify initial ray, because in order to have an angle, you need two rays. And the natural distance, the connection line, the line connecting point P and point O is one ray, one line. And you need one more ray compared to make the angle. So we have the initial ray combined with our terminal ray. Together, that's a angle theta. So we consider angle as if you rotate from the initial ray to this relation to the ray OP, what is that angle? So a positive rotation will be counterclockwise, a negative rotation, negative angle will be clockwise rotation, clockwise angle. Right? We practice identifying some of the key points. So went over one by one. A is distance 1, distance equal to 1, angle equal to 45 degrees. The second point is distance is 1.5 to the O, and then the angle is pi, which is 180 degrees. So from the initial ray to the ray OB, the angle is 180 degrees. And the third point is point T, the distance is 2, the angle is negative pi over 6. Because it's negative, we rotate clockwise. The last point, the distance is -1, the angle is pi over 4. So if you rotate positive angle pi over 4, and you're going away from instead of the angle pi over, but away from the pi over 4, then the distance of -1. So that one illustrate how do we use negative radius when we have a polar coordinate. All right, so now that we mentioned how do we use polar coordinate to represent points, and remember we can still use rectangular coordinate to represent points. So we have to understand both of them are working. The same point can be represented by polar coordinate. You can also represent it using rectangular coordinate. The two coordinate systems can be it's convertible from one another. So this is the conversion. So if you have polar coordinate already, to convert to rectangular coordinate, x value equal to r times cosine theta, y value equal to r times cosine theta. The foundation of this equation is from the right triangle trigonometry. Because cosine equal to x over r, sine theta equal to y over r, that's opposite over hypotenuse. We're able to reverse it to calculate the x value and y value. Second kind of conversion is convert from rectangular coordinate to polar coordinate. So if you already have the x and y, you want to find the r and theta. Now the r is equal to r squared is r squared equal to x squared plus y squared. Depending on do you want a positive r or negative r. If you want a positive r, then r equal to square root of x squared plus y squared. If you want a negative r, then r equal to negative square root of x squared plus y squared. So r can be calculated based on what you need. Theta is different. Theta, you can form a triangle with y being the opposite, x being the adjacent. So tangent theta equal to y over x, that's for sure. But then theta itself, depending on the quadrant, if the point is in the first quadrant, then the angle should be positive. So then theta equal to tangent inverse y over x. Now, if the point is in the second quadrant or third quadrant, then tangent inverse y over x is not going to work, because tangent inverse only cover angle in the first quadrant and fourth quadrant. So if you have second quadrant, third quadrant points, you have to plus pi. So you have to do pi plus tangent inverse y over x to calculate the angle. Last thing is if the point is in the fourth quadrant, tangent inverse give you a negative angle, but sometimes we would want to have positive angle, and then you have to add 2 pi. So fourth quadrant points, we would do 2 pi plus tangent inverse y over x together. So the angle calculation tends to depend on the actual quadrant of the point. Right, we have an example on all these conversion. So start with polar coordinate to rectangular coordinate. Question number 1, you follow strictly the formula x equal to r cosine, y equal to r sine to calculate your x, y. That you follow the formula strictly. You should be able to find the right value for x and y. And that was the first example. If the point in polar coordinate is 2 pi over 3, then the x equal to 2 times the cosine 2 pi over 3, which equal to -1. The y equal to 2 times sine 2 pi over 3, which equal to root of 3. So that's the calculation for the first point. The second point is -1, 5 pi over 4. So x equal to -1 cosine 5 pi over 4. We get root 2 over 2. Y equal to -1 sine 5 pi over 4. So we get 2 over 2. So these are calculations. Apply the formula x equal to r cosine theta, y equal to r sine theta. The second direction, we look at converting from rectangular coordinate to polar coordinate, which means you have to calculate the radius. You have to calculate r and then calculate theta. The first one is 1, 2. 1, 2 is in the first quadrant. So the radius is square root of 1 square plus 2 square. We get root 5. So r equal to root 5. And then theta. Tangent theta is 2 over 1, y over x. So theta equal to tangent inverse 2. So that's the calculation of the radius and angle. That one, because it's in the first quadrant, the angle is not too hard to find. The second one is point -1, 1, which is in the second quadrant. Radius calculation gave us root 2, r equal to root 2, because x squared plus 1 squared 2. Now the angle, because it's the second quadrant, the tangent inverse of -1 give you -45 degrees. But we don't want a negative angle. Negative angle is in the fourth quadrant. Make it into second quadrant, you have to add pi or add 180 degree. So -45 plus 180 is 135 degree or 3 pi over 4. So that's how we determine the angle. So like I said, to determine the polar coordinate, you have to find the right angle. And the angle has to depend on the quadrant. Let's keep that in mind. All right, so we're moving on to polar function. Now, if x and y can create function relation or graphs that is in the rectangular coordinate system, and then r and theta can construct equation in polar coordinate system, and that also can be represented as a graph and representing relation between dependent variable and independent variable. So there are some common equations. For example, r equal to 1.5 represent a radius 1.5 circle. Then theta equal to pi over 4 represent an angle of pi over 4, a line angled at pi over 4. Here are the graphs for both. Right. So then when you have a polar equation, one of the things you want to recognize is what exactly the shape of the image, the graph. Right. And then there's we went through a couple of examples on graphing. If we want to graph this polar function, we're going to identify a couple points for the angle, and then we want to graph them. And in this calculation, there's only 5, but when you actually graph it, you need more than 5. I use symmetry to graph 10 points instead of 5 points. Here we are. Those are the points, and connecting those points, you end up having a heart-shaped picture. The picture for r equal to 1 plus cosine theta. And this kind of picture, it works better with polar coordinate compared to rectangular. So when we talk about parametric equation have its purpose that cannot be achieved with rectangular coordinate system. So it's the polar coordinate. So our image that is really easy to construct with polar function compared to rectangular function. Right, another example of this one, we can graph it. I think I did it point by point. to end up having a lot of different points. Because we partition 0 to 2 pi and to 17 points, we end up having these. Once you connect it, it looks like a heart shaped, a flower shaped, four petal rows. So I also trace the whole graphing process using all those coin I graphed it by enlarging the range of the angle when I'm having the polar curve. So this is a more of a computerized graph of r equal to cosine 2 theta. So r equal to cosine 2 theta end up being a 4 petal rows. The reason that the number petal is double, if you see, you have a 2, but cosine 2 theta actually is 4 petal rows. So is the sine 2 theta is also a 4 petal rows. If you graph a sine or cosine 4 theta, you're going to have 8 petal rows. So whenever you have even number multiplied by the angle, the number of rows are doubled. But if you have odd number, so such as cosine 3 theta, you're going to only have 3 petal rows. So when it's odd number multiplied by the theta, when a trig function, the sine or cosine, we only have odd number, that exact number of rows. But when it's even number, the number of rows is doubled. I guess that's one of the patterns we can observe. This is where we stopped, and we stopped at how do we convert from rectangular equation to a polar equation to understand relation between the function. We went over the first kind, how do we convert from rectangular coordinate to polar coordinate. And because we got equation, we have equation saying x equal to r cosine theta, y equal to r sine theta. So you can always replace x in the equation. Whenever you see an x, you replace it by r cosine. Whenever you see a y, you replace by r sine theta. So the conversion from rectangular coordinate to polar coordinate should be followed by that conversion, followed by a direct substitution. So I did this one, y equal to x squared. So y replaced by r sine theta, x replaced by r cosine theta. Right there, that's our polar equation. So you can see y equal to x squared is a rectangular equation, which has only x variable and y variable. R sine theta equal to r squared cosine squared theta. There's no more x or y, just r theta. But typically, we would prefer having a independent variable in the formula, but then the dependent variable, you want to isolate it. So in this case, theta normally considered independent variable, r is a dependent variable. So we want r equal to a formula of theta. We have to solve the r. So that's something something addition to the conversion. After you convert it already into polar coordinate, you want to solve the r. So we have a better formula for the function. So we divide both side by r, which we end up getting this, and then solve for the r. We have r equal to sine theta over cosine squared theta. And in this case, we cannot have the denominator equal to 0. You can see cosine theta would equal to 0 for pi over 2 and negative pi over 2. So in the domain of the function, we are limited in between these two. The endpoint of the interval is undefined. Any question? So cosine theta, sine theta is well defined, but when you have a division, you want to watch out the denominator cannot equal to 0. So that kind of limited the interval of the function. So range. Right, so that's the answer for the first question, y equal to x squared. If you graph it with r equal to sine theta over cosine theta, it's the same picture. Also, you can barely see a whole problem in the representation, but it's a problem. All right, moving on to the second example, we have x times y. Remember, x equals to r cosine theta. We want to do conversion. Okay, somehow we don't want to do the conversion. This example, we want to convert it and see what it looks like after the conversion. Y equal to r sine theta. And then as usual, we want to, that's already a polar equation, but we want to convert it to have r solved. So solve for the r squared cosine theta sine theta equal to 1. So then the r equal to r squared equal to 1, division, r equal to the square root of the division. We have this. Right, that's the answer for the second question. Any question? All right, in this case, in this case, we can see that we have the limit to when cosine and cosine times sine has to be positive. That means it has to be in the first quadrant. In the first quadrant, cosine and sine are both positive. So the multiplication of sine and cosine are positive. Or it could be in the third quadrant. In the third quadrant, cosine theta is negative, sine theta is negative, so they multiply to a positive. So the picture of this function, just like the x times y equal to 1, then y equal to 1 over x. Y equal to 1 over x only have image in the first quadrant and third quadrant. Y equal to 1 over x. And look like this. Okay, because x times y equal to 1, right? So it can only be when both x is positive or when both xy is negative. There's nothing in here. But then the actual full equation reflects the same reasoning. All right, as far as the domain, you will have like a 0 to 2 pi open interval, and then you have pi to 3 pi over 2. Any question? So with every function, you have an equation to reflect the relation. You also have to possibly remember the domain is a concern for all formulas. So this is how to convert from rectangular component to polar coordinate. This is where we stopped last week. All right, let's look at how to convert from polar to rectangular coordinate. This is not as direct because to convert from rectangular to polar, we have substitution. X substitute by our cosine theta, y substitute by our sine theta. For this, you cannot do that simply because the conversion, the x is by itself, but then x is related to r times cosine. So you have to have r times cosine to replace by x. So that doesn't happen immediately. So then we have to work out the algebra and look for opportunity to do a substitution. So this is what we do. To start with question number 3, what we're going to do, the first thing will be multiply both side equation with the denominator, and we see this. Right? This process, whenever you say fraction, you multiply both side equation by the denominator of the denominator of the fraction. This is a common practice to make the equation less cumbersome. So this, when you take the equation number 3 and multiply both side equation, serve two purposes. Number 1, you would be able to get rid of fraction. Number 2, you can force the r and sine theta cosine theta to be together. Because only when r multiplied by sine, we see a y value. When r multiplied with cosine, we see x value. So r by itself and cosine theta sine theta by itself doesn't present opportunity for us to substitute with a different set of variables. Are we okay? Any questions so far? Okay, so from here, we're going to multiply out, okay? R is on the outside, it's a common factor. We multiply, distribute the R, and you have R times sine theta, R times cosine theta, and realize that in the conversion equation, we have x equal to R times cosine. So whenever R times cosine, you can replace that by x. And then when r times sine, you replace by y. So there we already have a substitution that will allow us to replace r or theta in our original form. You end up having this. So we will have y minus x equal to 2. And that's the equation relates the x variable and y variable. And there's no more r and theta after the substitution. So it's basically, we pretty much are trying to find way to substitute using the same set of relation, except they're not immediate substitution. That I think by the nature equation, you can see x is by itself. To substitute x is easy, but r times cosine, there are 2 variables in there, and these 2 are not always automatically together. That's why sometimes the conversion from polar to rectangular are not always straightforward. Any question? So we can see the number 3 in whole equation. We don't immediately see that's a line, but after the conversion, you see a straight line. Y equals x plus 2. It's a line relation. Or you can graph it. Graph r equal to 2 over sine theta minus cosine theta. You're going to see it is a line. That's our answer for number 3. After the conversion, the rectangular equation is y equal to x plus 2. I'm gonna move on to question number 4. Right, so solution for number 3, as you push to the left, let's look at this one. Okay, so again, we don't see how do we convert this, but what we can try is this is the equation. Equation can be changed. As long as we multiply both side equation by the same thing, it will follow the same equation. So that same equation, what we can do is we multiply both side equation by r. So if you multiply left side and right side of this equation with r, you have r squared equal to 2r cosine. The reason that we multiply by r, because cosine itself, we won't be able to directly substitute it. But if the cosine theta multiplied by r, that is already x, and x equal to r cosine theta. Okay, right? So from here, we can recall some of the substitution method. Right, this is some of the things that are common. X equal to r times cosine theta, y equal to r times sin theta. And also, whenever you have r squared equal to x squared plus y squared. So we will substitute the r squared by x squared plus y squared. We'll substitute the 2r cosine theta with 2x. So that's something we see in the conversion between the 2 points. So in the point conversion, we have this. In the conversion of the equation, we still have that. Any question? All right, so this equation have x squared plus y squared. Summation 2 squared integrate 2 equation represent a circle. So x squared plus y squared equal to 2x. It's a circle. I think the center is at 0.10. Any question? Right, if you want to convert it to a rectangular equation to identify the center of the circle, you can move the 2x over. X squared minus 2x. I plus 1 would make it into x squared, x minus 1 squared, and then there's actual 1 on the right side equation. So this is a circle with radius 1, center at 0.10. So after completing a square, we can identify the center of the circle is at 10. The radius of circle is also 1. So the rest of the algebra, just try to identify the shape. Any question? Right, so this is the example on how to convert between the two set of coordinate system, point conversion, point to point, or conversion equation to the equation. Any question? A couple of homework are going over the similar thing. All right, the rest of the this section is going over different type of the polar equation to represent different shape. The first one is different kind of circle that goes through the origin. You see the origin is at 0, 0. Okay, just want to make sure it actually shows everything. All right, so top one, you see when you have cosine, r equal to cosine is a circle going through the origin, but it's on the right side of the origin. The r equal to negative 3 cosine or negative 2 cosine is a circle at the left side of the origin. Now, r equal to 2 sine theta is a circle on top of the origin, and then r equal to negative 3 sine theta will be a circle that is below the origin. So basically, whenever you have r equal to a number times cosine, is a circle on the left or a circle on the right. If you have r equal to a number times sine theta, then it's a circle above or circle below, depending on whether it's sine or cosine. If the number is positive, it's above. If the number is negative, it's below, it's sine theta. But for cosine, the number positive is on the right, the number negative cosine is on the left. The number we multiply tend to affect the size of the circle. Okay, so for example, 2 times cosine theta, the 2 is the diameter, the radius is 1. Right? If it's negative 3 cosine theta, the 3 is the diameter. The negative 3 only indicate the direction. So basically, cosine follows the x value, the sine follows y value, positive, negative. Are we okay? All right, so this is just to illustrate some of the common polar curve. So the textbook, we did mention this. So when you have a circle centered on the x-axis, you have the number multiplied by cosine theta. And whenever it's a number multiplied by cosine theta, you have a point going through the origin, but your center is at here or here. So A being positive or negative affected whether it's on the left or on the right. For r equal to a times a number, if A is a number times sine theta is either a circle above or circle below, depending on whether A is positive or negative. Also, the A would be, the size of the A will be the diameter. So those are the two that we kind of illustrated with those examples. All right, and the last one, if it's centered at the origin, then all you have to do is identify the radius. So r equal to a as center at the origin, radius equal to a. All right, this a could be positive or negative, which doesn't make any difference. So r equal to 2 represent a circle of radius 2, but then r equal to negative 2 is also a circle of radius 2. So in this third example, for r equal to a number, that number being positive or negative would be the same shape because it's cover all the angle, okay, the angle. If it's negative, it goes opposite and on the other. Okay, the last scenario is r equal to a function of theta, which represents different kind of spiral. Depending on the function of theta, it kind of affected the I guess the radius of the spiral. If you have a quicker theta, then the spiral is more expanded furthermore. I guess I can show an example. All right, so for example, r equal to theta. So this is r equal to theta, right? And then, for example, you can also have r equal to 2 theta. Okay, so you can see the radius increase bigger. I guess let me remove the grid. All right, and then let's remove that one and compare with a bigger increase. So r equal to e to the theta. It's also a spiral, but then the radius get way bigger. I guess the exponential function is increase way faster than trying to illustrate how things are changing there. That's the little spiral we have r equal to theta. I find that kind of interesting to say the size of value being affected, right? So here is a spiral for r equal to theta. You can have r equal to say theta squared. So this is the spiral. See different kind of spiral motion there. Anyway, just want to explain that with polar coordinate, the spiral doesn't have to be just that single one. There could be different kind of spiral if you want to define design your own spiral motion. All right, and move on to another set of polar equations. So we had here, you see, if you have r equal to number, it's a circle center at the origin, but if you have r equal to a number times sine or cosine, you have a circle at the side of the origin. But when we combine them, like r equal to a number plus a number times sine or cosine, what will happen there? What will happen is this, okay? So here, if you have, it could be cosine or sine. Now, the difference between cosine and sine is cosine is on the left or on the right, left or right of the origin. You see all these examples are having the shape to the right of the origin, but you can very well change that beam to a negative number, and it'll be on the left. I mean, you say the direction can change all the time. If you change it to a sine, r equal to a plus b, a number plus b sine theta, then it will look like a upper, like a heart, this shape instead of that. So just the orientation could change. All right, so this is called lemma-sum. It's different type of lemma-sum depending on the relation between these two numbers. The first example showing that the A has a smaller coefficient than A is less than B. So B, which is the one to the side, B is bigger than A. All right, and then this one on the side has a bigger impact. You can see a little loop, inner loop. The lemma sum was the inner loop. Now, if the A and B equal to like 2 plus 2 cosine theta, you're gonna see a heart shape, which is called cardioid. Then a third example is when this is A bigger than B. So this one is bigger. So when A is bigger than B, see, remember R equal to A represent a circle with the origin being the center. Then when A is bigger than the B, then this outer circle has a bigger impact. So you only see a little dimple at the side. And the last example is when A is way bigger than B. We're saying A bigger than twice B. Okay, you pretty much say a bigger, majority of it is a circle around the origin. Because the circle with center and origin has a bigger impact. So it's almost like try to compare R equal to A is a circle. R equal to B times cosine theta is a circle, but it's to the side. And then when A is bigger, R equal to A, it controls the overall shape with a little change caused by that side. But when B is bigger, this one is the side, and this one causes a like impact the shape more. I hope that kind of makes sense. So essentially, it's a combination of the two. I think I was giving a couple of examples, right, to what we have here. That's a cardioid. We have 2 and 2. So I'm trying to illustrate the sign. If you have 2 plus 2 cosine theta, the cardioid look like a part. So if it's a plus, it would be on the right, like it's always a cosine. If you have negative, the negative cosine is on the left of the origin. Over here is when the R equal to 2, which is the A, is way bigger than the B. So in this case, R equal to 2 will be a circle of radius 2, and the cosine only changes slightly because the cosine has a smaller coefficient. Are we okay? That's the one that's the alignment sound that has a bigger coefficient. That one. On the other hand, if the trig function has bigger coefficient, like 1 minus 2 cosine theta or 1 plus 2 cosine theta, we see a alignment sound with the inner loop. Because what are we on this side is a bigger value. Yeah, you almost kind of like to see 2 little circles to the right of the origin. Any questions? Right, so we'll just use the example to illustrate the 4 different scenarios. This is the A less than B. This is the A equal to B. This is A bigger than B. And this is A bigger than twice of B. Relation between A and B in this lump sum graph question. We don't study this a lot, but at least knowing some of the common pictures, special curve and polar curve, it show up in other classes. That's why they have a special name to represent a collection of all these polar curve that has similar features. All right, and this is the one I was mentioning earlier. These are called Rose curves. All right, so when you have double angle or higher number angle inside the trig, so cosine higher number of theta or sine higher number of theta, it has the Rose curve. So earlier we have cosine theta, sine theta, but you only have a single theta in the trig, like this, all right? Or this. But now we look at what if we have a number multiplied to a theta and it has other pictures. If the number we multiply is an integer, and that integer affects how many petals we have, if the even number multiplied by theta, then you have to double that number so that represent the number of roses. For example, cosine 2 theta have 4 petal rose, sine 2 theta is 4 petal rose. Cosine 0 equal to 1, so you can see the x-axis is 1, 0 there. But sine theta equal to 0, so sine starts from 0. So then they have different shape. Even if the cosine 2 theta and sine 2 theta is being compared over here. On the other hand, if it's odd number, so such as cosine theta, 3 theta, or sine 3 theta, then you have 3 petal rows. So if it's odd number, that odd number is the number of rows, so we don't have to double the number. to represent the number of roses. Any question? Right? So it's using a couple examples. These are representing, this is the sine 5 theta, cosine 5 theta. So you can also try cosine 7 theta, sine 7 theta on the decimals. You see that if it's odd number, that represents exactly how many roses, how many number petals in your rose. And if it's an even number, then you have to double that number. For example, sine 4 theta have 8 petal roses, but cosine 4 theta also is 8 petal roses. So then it draws symmetric curve really easily using the polar curve. Any question?
I see that sin 4 theta and cos 4 theta, if you overlay them, they both match. But cos 5 theta but there's like they're rotated in the right alignment, so it looks like a nice even distribution.
Yeah, so the shape.
But 5 theta and 5 theta are off angle.
I think they are the same. Because for cosine, if you have cosine 0 equal to 1, cosine has to start there.
Yeah.
So then it rotates and then spheres and then back here. But the sine is 0, but then sine pi over 2 is 1. So sine has to be 1 right there. That's why you have to have that one. The rest of them kind of follow without the center is. Sine has to be symmetrical about the y-axis, but cosine is symmetrical about the y.
Yeah.
So that one and that one is the one that kind of controls all of these.
Yeah, that makes sense.
For cosine 4 theta, theta has to be 1 before sine theta. Sine theta, I don't see a 1
For
anymore.
the even ones, they're symmetrical both axes, aren't they?
Yes. For the even one, yes, they have to be symmetrical either way, but for odd number, we only control the min value. For cosine, you have to have cosine 0 equal to 1, but for sine, you have to sine pi over 4 equal to. And sine pi over 2 equal to 1.
Is there a way to rotate the petals?
I guess you can turn from sine to cosine that already is a rotation.
Well, more specific rotation.
Yes, I think if you do like theta minus the angle, that will change the rotation. Just like when you have y equal to x squared, y equal to x minus 2, you move it 2 units to
So
the
it's like a
right.
transformation.
Yeah, it's almost like transformation. If you want to rotate it, you have the angle minus the whatever your rotation you want it.
Okay.
We are moving on to the kind of graph. All right, so how do we represent lines? If you have a line going through the origin, all you have to do is theta equal to that angle, so theta equal to angle already representing the line, but this line will always go to the origin. If you represent a line that's not going to the origin, then you have to look at what exactly equation that we have. So if it's a horizontal line, then like y equal to a. If y equal to a, then y equal to r sine theta. So r equal to a over sine theta, which is a times cosecant theta. If it's a vertical line that's x equal to a, the vertical line x equal to a, x equal to r cosine theta, so r equal to a over sine theta. A over cosine theta is a times secant theta. So that's this represent horizontal line and vertical line. But if it's a line at an angle, then you have y equal to mx plus b. So what is the y equal to mx plus b? This r sine is y, mx, x is r cosine theta. So y minus mx equal to b. So that we factor out the r, so it's r equal to b over sine theta minus m cosine theta. So this is the equation of y equal to mx plus b presented that way. There's a b and there's an m. Any question? You can almost connect that with the rectangular equation if we multiply the denominator. This is how we use polar equation to present line. Typically, polar equation is not good at representing line. So when we study equation of line, we normally will convert it into rectangular equation instead. So it's when the trig equation being applied, then polar can create things that cannot be done with rectangular equation. There are a couple of special curves. Number one is if you have fraction of angle, what will happen? So here we have theta over 5. So you have 1/5 theta instead of sine theta or sine 5 theta. We have sine theta over 5, which looks like this. Okay, now this is a times sine 2 theta over 5. If we compare these two, this one, if we have even number theta, remember when you have even number theta, it causes the function to create a symmetry. So over here, we don't see any symmetry in the sine theta over 5. We already see some symmetry when we have 2 theta over 5. Also, you can identify the layer of the inner function, outer function. You have 1, 2, 3, 4, 5. So the denominator reflected how many layers in the whole picture. I also did a couple other fractions to say when we have fraction in the trig, what will happen? So here we have, I used 2 theta over 3 because I want symmetry. If you have theta over 3, there's no symmetry. So 2 theta over 3. We have symmetry in the polar curve, and then you see the 3. 3 represent the layer of curve. This layer, inner layer, the star. 1, 2, 3, there's 3 layers, denominator 3. I went over to 2 theta over 7. And you can see different layer of the picture. 1, 2, 3, 4, 5, 6, 7, 7 layer. If you want to try to study or try to see different example of polar curve to see how the denominator of the fraction affecting the image of the polar curve. This one is theta over 7, so it loses the symmetry because numerator is odd number. We still see 1, 2, 3, 4. I don't see as many because there's because of the loss of the symmetry, they kind of take care of the layers. So there's a less layer function. Another thing is to see the entire picture, you need to have a bigger range. So we cannot do 0 to 2 pi because if you only graph these functions between 0 to 2 pi, you only see a really small part. For example, the middle one to have the entire image of symmetry, you have to go from 0 to 14 pi, which is like 2 times 7, 14 pi. For this one, I went all the way to 8 pi. I'm not sure if I made a mistake or not, but because it's a 2 theta, you have to have even number. I think it should work as well with 2 times 3, 6 pi should be enough for the first image. This one, I did 7 pi. I think that goes with the denominator. So the length, the interval that you're using for graphing is very important. You have to adjust that. I mean, if you're not interested, then I guess it's just an example of these special curves. But if you want to do possibly some math research, maybe this will be useful, depending on like interest. Anyway, this one called Lemniscate is a squared times cosine 2 theta. So because we have cosine 2 theta, there it reflects the symmetrical virtually and horizontally. But then the thing is on this side we have r squared. Okay, so if we don't have the r squared, if it's just r equal to a squared cosine 2 theta, it will be a 4 petal rose. So having that r squared there kind of get rid of the upper part and the lower part. So the r squared is one of the main change compared to the 4 petal rose picture we had earlier. And this is r squared, a squared sine 4 theta, cosine 2 theta. It maintained the same shape. I guess the secant to the 4 theta multiplied changes the shape, but the structure will be the same. The shape is a little bit wider because the secant that we multiplied. Anyway, any question? We were not gonna use all of these, just try to use a couple examples to kind of showcase what polar curve can do. Look at a different fraction, different combination of coefficient. And that's pretty much introduction of polar curve and polar equation. Any question? This side of the assignment is already done. If we look up woodwork, the common example on polar coordinate would be Assign a lot of work on this. The first question is to okay, so this is identify a single point on the polar curve and write different coordinates for it. Trying to at least go through the first one or two examples. All right, if we look at it, you can see the original curve is this. And remember, r equal to 12 represent a circle of radius 12. R equal to 2 cosine theta represents a circle of diameter 2. So the 12 is way bigger than 2. It will reflect a picture like this. The little dent, because that one controls the main shape. So like a big circle with a little dent on the side, and that one has a very small coefficient, so it only causes a small dent at the side of the circle. So we say that we have a point, we really focus on that point, say they equal to 26 pi 24. Number one is find the polar coordinate for this point. We already have the angle for the polar point, which is, I mean, for a polar coordinate, there's the theta, which is an angle, and there's a radius. So the question says all we have to do is calculate the radius, and the radius on this polar curve follows that equation. So all you have to do is 12 plus 2, and then cosine. This is radius equation, cosine 24 pi over 24. So then the first question is, since we're talking about a point, the radius for that point with r being positive, I'm not sure this is positive though. So this point we already kind of see. The angle is 26 pi over 24. And the radius is this number. Radius is 12 plus 2 cosine 26 pi over 24. So the radius is kind of big and the angle is big. The question says we want to have theta between pi and 3 pi over 2. This is already in that range, so the answer should be fine. So when we answer, I'm trying to look at the angle. So it's 12 plus 2 times cosine 26 pi over 24. 26 over 24 is a little bigger than 1. So it's, the angle there is slightly bigger than pi, bigger than 1 pi. So that was the first question in this question. Part A. Part B is find the rectangular coordinate. That's our radius right there. So it's radius multiplied by cosine theta to give you the x value. Same question. This is our radius, and we multiply by cosine of the angle, which will be 26 pi over 24, right? And then that's the r times cosine theta, and then the y value should be r times sine theta. Okay, so this is how we convert from polar coordinate, the r and the theta, into rectangular coordinate, which will be r times cosine for the x and r times sine for the y. There. Okay, the question says how many times does a curve passes through the origin? We mentioned the shape of the picture. There's a 12. I don't think the picture passes the origin at all. So for example, if the picture passes the origin, you have to have radius equal to 0. So can we ever make it into a 0? It's 12 plus 2 cosine theta. That is the r, right? So no matter how small, no matter how you change the theta, 2 cosine theta between -2 and +2. So the radius will be between 12 minus 2 and 12 plus 2. The radius between 10 and 14. So the radius will never be smaller than 10, right? So the radius is always positive and it's never going to pass through the origin. So 0 time. Are we okay? So you can also graph it to see how many points it passes the origin. I would say 0 time it passes the origin. And we can graph it to tell what it would look like in this image. So what does it look like? You can graph R equal to, let me try to show. R equal to 12 plus 2 cosine theta. So that's how it looks like. You see, it's almost like a circle, circle of radius 12 because this 2 cosine theta, the 2 is smaller than 12. So then the 2 cosine theta, it's like you're having a really big radius, and then here you have something that's just slightly change a little. So kind of move the cosine a little to the right, but then overall it's a circle, right? Are we okay? So that illustrated one of the relation between the coefficient and the limit cell. When this one is much bigger than that one, you only see a circle. We don't have that much of an impact on this circle. So this improves also the origin at all. I think origin here, the curve itself passes the origin. That's my first example. Second question, this. Right? So represented by either a circle or ring or sector. This first question says R is between 0 and 1 and angle between 0 and 2 pi. So it's a circle, right? It's a circle of radius 1. So that's C. Second saying the R is between 0 and 1, radius between 0 and 1. So within circle 1. And then the angle between negative pi over 2 and positive 3 pi over 4. So we're going to look at these kind of sectors. Negative pi over 2 is this. To positive 3 pi over 4 is this one, right? The E. Negative pi over 2 all the way to 3 pi over 4. So the second picture matches E. Understanding the polar equation. The radius is between 0 and 2. So it's a circle of radius 2 bigger, this one. And then the angle between 3 pi over 2 and 2 pi is H. Are we okay? So maybe I don't have to finish the whole thing. All right, if there's anything new, that was a ring. That's when the radius between two numbers, like this one is ring A. It's the whole ring, 0 to 2 pi. Now this one, you're gonna see a ring, but the angle is from pi over 2 to, this is 3 pi over 2, that's pi over 2. So this is going to be the D. Like partial of the ring. Are we okay? I'll let you finish the rest of them. I only finished some of the questions. 60%, so I leave a few questions for you to finish the rest. Any question? Even 10% for 2 to 4 correct, 60% for 5 to 6 correct, 80%. Okay. All right, so that's the couple examples from the polar corner question, and try the rest and let me know if you have questions. All right, in the meantime, I'm probably gonna move a little bit forward because I feel like we're a little bit behind schedule. So let me start a little on 9.5. All right, kind of like the relation between 9.3 and 9.4, we study parametric equation in 9.2, and then we do calculus in 9.3. Right, so 9.4 we talk about introduce polar coordinate, and then in 9.5 we talk about calculus with polar curve or polar functions. So how do we do calculus? Number one thing, we need to know how to find derivative. Okay, so how to calculate derivative with polar function? In polar function, we don't have y value or x value, but we can convert it to. So by derivative, we're still looking at our x value and y value because slope is better understood if we have the rectangular derivative. So our goal is to find a rectangular derivative. So Number one, you turn from whole equation to a parametric equation. R equal to a function of theta is a polar function, but x equal to r cosine theta, y equal to r sin theta. The r can be replaced by whatever polar function you have. So if r equal to f theta is a polar curve, like r equal to 2 sin theta will be a polar curve, but so here is 2 sin theta. And you multiply cosine theta, sin theta to turn it into parametric equation, and we're basically applying parametric equation method for the calculus part of it. But maybe polar curve has their own solution. So ultimately, we will find dy dx using derivative of y divided by derivative of x. That's how we find dy dx. So that's the basic idea, and we can try to look at how it's calculated. Now, the y has multiplication, so we have to do the product rule. The x, we're going to find derivative of x, the x of the f theta cosine theta. So to differentiate the x, we're going to find f prime cosine theta plus negative sin theta times f theta. So then you have a product rule. That's why we have summation in the numerator and denominator. So that's the dy dx for the polar equation. So it looks a little bit wrong because we did apply product rule when we try to differentiate the y. So f prime times sin theta, that's differentiating this factor plus keeping the f, differentiate the sine and cosine. Now the x function, x equal to f theta cosine theta, f theta, hypothetically f theta. So we have f prime multiplied by cosine, and then keep the f and differentiate the cosine, the derivative cosine is negative sine. So that's going to be the format how to find dy dx in the with the polar function being introduced. So that's going to be our formula with the polar curve. So let's look at an example on how do we do this. So this is the example. We have a limit sum that says 1 plus 2 sin theta. In this question, the 2 is coefficient of sine. So this is bigger than the 1. So that means you only have a really small circle. R equal to 1 is a small circle, but the R equal to 2 sin theta is a bigger circle. In this case, the 2 bigger than 1 is forcing a loop. So this will be the limit sum that has a little loop in the middle. And that's what's being more confusing about it. It's probably have a lot of horizontal tangent line, vertical tangent line. So question number 1, we're going to find the tangent line and normal line to this polar curve. And number 2, we want to find a vertical tangent line and horizontal tangent line. So let's reaffirm the idea. In this question, we're trying to understand lines. But lines are very difficult to study if you only use polar equation and polar function. So we're going to convert back to the rectangular form because rectangular form of line is easier to handle. So this is the reason. Rectangular form is better at representing lines. Therefore, we are converting it into the equation of a rectangular coordinates. So there's a conversion of it. Number 1, I convert the point to a rectangular equation. I didn't convert the point. I should. Right. We should do the r times cosine theta and r times the sin theta to convert it to a rectangular coordinate. All right. Let's look at the slope. To find slope of the line, you want to find the derivative, and then you find the value of the derivative to find the slope. So this is say x equal to r equal to 1 plus sin theta. But to find the x value, you have to have the r multiplied by cosine theta, the y also equal to r times sin theta. So then that is a complex version of x and y, and now we have to find the derivative. Derivative of the y, you see we do product rule. That is the derivative of 1 plus cosine, 1 plus 2 cosine, 2 sin theta, derivative is 2 cosine, and multiply by sine. And then you keep the 1 plus 2 sine and find derivative of the sine, which is cosine. So applying product rule. For the x, you can find derivative of the 2 cosine is derivative of 2 sine is 2 cosine. 2 cosine times cosine is 2 cosine squared. And now we want to keep the 1 plus sine and find derivative cosine. Derivative cosine is negative sine that we have. So the entire calculation is finding derivative x, which goes in the denominator, find derivative y, which goes in the numerator. This calculation, do you have any question? We're trying to use the derivative to find the slope of the line. Question. Right? So we're gonna focus on the point when the angle equal to pi over 4. So when theta equal to pi over 4, the dx equal to negative 2 root 1 to root 2 minus 1. So that's gonna be the slope of the line. And the point of the line, we should do the radius multiplied by cosine theta. So this one multiplied by cosine pi over 4 for the x, and this radius multiplied by sine pi over 4 for the y value. So the tangent line looks like this. Tangent line slope. The slope is that number, we should really, it's easier with the decimal. The number is actually negative 3.83. Negative 2 root 2 minus 1 is negative 383. And then the x value is from r cosine theta, calculated from r cosine theta. The y value here, y is 1 plus root 2 over 2, calculated by r sine theta. So that's the equation of tangent line. Once we have the point, we have the slope. Equation of the tangent line. Any question? I did work on the detail for the calculation, right? So the dy dx, if you clear, distribute the term, we would end up having cosine theta times cosine theta, then the 2 cosine theta sin theta plus 2 cosine theta is 4 cosine theta sin theta, and there's a cosine theta there, there's cosine squared, minus sin theta, and then minus 2 cosine squared. So we simplify the dy dx and plug in pi over 4. Cosine pi over 4 is root 2 over 2. Sine pi over 4 is also root 2 over 2. So the cosine square is 1 over 2. Sine square is 1 over 2. So the derivative calculation will be the numerator. This is 4 times 1/2. That was 2. And cosine theta is root 2 over 2. And then the 2 cosine square is 1. This cosine square is 1/2. Right, so this is just assist the calculation. We have this. The denominator have 1 minus 1 that actually equal to 0. So denominator is a single number. Notice that if you multiply root 2, 2 times root 2 is 2. 2 over 2 is 1. So we could multiply denominator and numerator by root 2 to get rid of the roots. There's only one number in the root, so it's easy to get rid of the roots. And then we have this. So that is proof the slope equal to negative 2 minus 2, which confirm what we already have. Now what's that? You can see that was the slope calculation. I could just try to reaffirm the slope calculation with a little bit more detail. Any question? And then 1 plus root 2 over 2 is the x value. The x value and y value are equal to the same thing because it was pi over 4. On the line of pi over 4 is 45-degree angle. So at 45-degree angle, the x equals y. The normal line would be the same thing, except that one is negative 3.83. So for the normal line, this one, it will be a positive 1 over 3.83. The rest is the same. I'm trying to determine normal. So then after simplifying, combining the term, we have this normal line. So this is our first example using the formula to find the normal line and tangent line. The second question is to find where do we have vertical tangent line, where do we have horizontal tangent line. We can start with the horizontal tangent line. When we have horizontal tangent line, the slope equal to 0 means that the derivative equal to 0. See, the derivative is in the fraction. So for the derivative equal to 0, this fraction equal to 0 only when the numerator equal to 0. So there we have the numerator equal to 0. Now we need to solve for theta. And their common factor cosine theta. So you factor cosine theta, you have 4 sine theta. So cosine theta equal to 0 or 4 sine theta plus 1 equal to 0. Now, we need to know when with the cosine equal to 0, within 0 to 2 pi. And I draw a unit circle just to study the cosine value. Within 0 to 2 pi is 1 cycle, and cosine theta is cosine value follow the x value. So cosine is 1, 0, -1, back to 0, back to 1. That's 1 cycle, right? So cosine equal to 0 at 90 degree, cosine theta equal to 0 at 304. So cosine theta equal to 0 has only two solutions within one cycle between 0 to 2 pi. That's two solutions, pi over 2 and 3 pi over 2. So for cosine theta equal to 0, we are really solving a trig equation. Any question? And then we move on to the 4 sine theta plus 1. You see when I'm solving for value where the horizontal tangent line exists. So for that, you would solve the plus 1, you minus 1 to the other side and divide by 4. So sine theta is negative, sine theta is negative 1 over 4. We could solve a solution. Sine theta is negative 1 over 4. So theta should equal to sine inverse negative 1 over 4, which is negative 0.2527. But that's not going to be a solution because we're looking for solutions from 0 to 2 pi, 0 to 6.28. So that angle is too small. It's in the fourth quadrant. So for sine to be negative, we study the unit circle for sine. Sine follow the y value. So 0, 1, 0, -1, back to 0. So that's the sine value. Sine is positive in the first two quadrants, negative in these two quadrants. For the sine to be negative 1 over 4, there's two solutions. It's over here or over here. This negative sine inverse negative 1 over 4 is in the first quadrant. Fourth quadrant, that's not the one we're looking for in the third quadrant. So the solution should be the number that we find. You add 2 pi to find the fourth quadrant solution. You add 2 pi, add a pi plus the sine inverse of the one you have there. That's the other two. We could probably review this tomorrow. That's the today. Sorry, maybe a little bit. Try your coordinate homework. If have questions tomorrow.